Thank you very much. As I said on Thursday night at the awards ceremony, the best kind of award for a developmental psychologist to win is a Lifetime Achievement Award, particularly one that's associated with William James. I want to start by showing a videotape to give you some idea of the phenomenon that I'm talking about. This is a man who was asked to reason about a moral dilemma. And his speech is a little esoteric, a little abstract, but I want you to focus on his gestures, which in fact I find much clearer. They concretize his ideas and make them clear. He talks about two ideas come into competition, and when they come into competition, that's the moment of negotiation.
With him, I cannot communicate verbally yet. He's only 4 months. And when I think about opportunities like this where you have two interests that compete with one another, this is the point where people develop the skills of negotiation. Even with my young son.
Okay, so there's gesturing that's making these abstract ideas pretty concrete. There are other situations in which we gesture. We all know we gesture when we give directions. In fact, we can't give directions without gesturing. So watch this woman who was asked to say how she gets from one place to another.
But not least, how about from home to Ashton?
Okay, well, Ashton, we go left and then out to 3rd, and then up to Jordan, then right again, and we go straight up to 10th Street, but we turn right on 10th. So Jordan is actually, which would be like right here, it's behind us instead of crossing into the library. Mm-hmm. So we go right, and then we cross a driveway, which is to right quad, and then cross a street called Sunrise, and then Ashton is we keep going a little bit further, and Ashton, you turn right to get to Ashton.
Okay. Good.
So there's nothing unusual about this woman's gestures. She's very precise, she's very good, but there's something unusual about her that I bet some of you already noticed, which is that she's blind. And she's congenitally blind. She has never, ever seen a person gesture. But she gestures, and she does so when she talks. So what that suggests is the robustness of this phenomenon of gesturing. It also suggests that it's really tied to talking. And it's this phenomenon that I want to talk about today. And the question that I want to ask is whether these gestures are anything more than hand waving. And of course, the answer I want to give is yes, because if it were no, it would be a very short talk and not worthy of a Lifetime Achievement Award. So I want to first convince you that gesture reflects knowledge. And when it reflects knowledge, it can actually tell us who is on the brink of change. But gesture can do more than just reflect what we know. I want to argue that gesture can change what we know. So I want to spend sort of the first bit of my talk convincing you of these two things, but then I really want to spend most of my time trying to figure out what makes gesture a mechanism of change. Why does it work? Okay, so gesture reflects knowledge. To convince you of this, I'm going to go back to a phenomenon that Piaget made famous. This is study of conservation of number. So Piaget would take 2 rows of checkers and make sure that the child knew that there were the same number of checkers in the 2 rows. Then he'd spread one out, ask the child if the child thought it was the same number of checkers, and children who say no are called non-conservers. Piaget was interested in the rationale children gave. I'm interested not only in the rationale that they give with their mouths, but also what they say with their hands. So this is a non-conserver. She's convinced the number's different. She says they're different because you spreaded them out. She's talking about spreading in both her hand and her mouth.
Like this. Do these 2 rows of checkers have the same number of checkers? No. Which row has more checkers in it? Now, why does that have more checkers in it?
You spread them apart and this one stay like you put them down.
So this girl has produced what we've come to call a gesture-speech match, in the sense it's pretty much, not identical, but it's pretty much the same information, talking about moving in both hand and mouth. Contrast her with this child who says exactly the same thing. He thinks they're different. He says they're different because you moved them. But when you watch his hands, what he does is this. Nobody moved the checkers like that. That's really pairing up the checkers in one row with the checkers in another row, which is the beginning of one-to-one correspondence.
Do our rows have the same number of checkers in them now or different? Why is there a different number in our rows?
Because you moved them.
Okay.
So this child is produced, we've been calling a gesture-speech mismatch. He's talking about moving, but he's gesturing about one-to-one correspondence. There's different information in the 2 modalities. So when we found kids like this, we thought maybe they're in a different cognitive state from the matchers. So to find out, we gave them all instruction. They're all non-conservers. We gave them instruction and then looked to see who profited from the instruction. And what you see in this first graph is that the children who were mismatchers, who are represented in blue, are much more likely to succeed than the children who are matchers prior to instruction. So, children who produce mismatchers are ready to learn conservation. Just 5 to 8-year-olds. To find out, we looked at another task, a very simple one from an adult point of view. 3 plus 4 plus 5 equals blank plus 5. Unfortunately, it turns out a lot of 4th and 5th graders in America can't solve this problem. Too bad. And when they make mistakes, what they do is either they tend to add up the numbers on the left side of the problem and put that number in the blank, or they add up all the numbers in the problem and put that number in the blank. But as we all know, I hope, what you're supposed to do is recognize that there are 2 5s that are the same, add up the 3 on the floor, and put that in the blank. Okay, right. So here's a child who added up the numbers on the left side of the problem and says that in both gesture and speech. She points at the 5, the 4, and the 3.
And how did you get 12 as your answer?
8 is 5 plus 4 plus 3.
Okay, she's produced a match. She's talking about the same strategy in speech and gesture. This one says exactly the same thing, but watch her hands. She points at the 5, the other 5, the 4, and the 3. With her gestures, she's talking about adding up all the numbers.
So how did you get 12?
I added 5.
You see the point of the 5?
And then the 3 too.
So she's produced a mismatch in that she's talking about adding up numbers to the equal sign with speech, but adding all the numbers in her gestures. We gave them instruction, did exactly the same thing, the data for conservation on the left, the math equivalence data on the right, and again, mismatchers are ready to learn. So what this suggests is that gestures conveying substantive information. This isn't about gesturing or not gesturing. They're all gesturing. And it's the nature of the information conveyed in gesture in relation to speech that's really important. And some of those ideas conveyed in gesture are not expressed in speech, which is why it gets interesting. So, can gesture change our minds? In order to convince you that gesture is changing our minds, what I'm going to have to do is manipulate gesture. So I'm going to manipulate the gestures that we see and also the gestures that a learner produces. So first, in terms of manipulating the gestures that learners see, we went to the classroom actually and we looked at what teachers do. And so we modeled our lessons after that. We had 3 conditions: either teacher produced no gesture, spoke but no gesture, matching gesture, or mismatching gesture. And I'll give you an example in a minute. Half the children got one strategy in speech. So they get this, what we called an equalizer strategy. I want to make one side equal to the other side. The first group got it only in speech. The second group got it in speech and gesture, a strategy like this. I'll show you an example soon. In the mismatching gesture, they got equalizer in speech, but add, subtract, a different strategy in gesture. Okay, so if you notice, the matching and the mismatching gesture conditions differ in the amount of information contained. So we needed to control for amount of information, so we also had groups that had 2 strategies in speech. This group has equalizer in speech and add subtract in speech. It's all same information, but all within modality, as opposed to the mismatching gesture, which is across modalities, and then we filled out the design to make it neat. Okay, so let me concretize it. Here's the teacher, Melissa Singer, whose work this is, who says equalizer in speech with no gesture.
Solve this by adding 7 plus 8 plus 5, which equals 20. And then we want to make the other side of the equal sign the same amount. So 15 plus 5 also equals 20. So 15 would be the answer. So now I want you to try solving it.
Okay, here's Melissa saying exactly the same thing, but what she does with her gestures is a match, an equalizer gesture, which we actually picked up from kids who know how to solve this problem.
That is, we can add 6 plus 8 plus 4, which equals 18. And then we want to make the other side of the equal sign the same amount. So 6 plus 12 also equals 18. So 12 would be the answer.
And here's the last one. She says the same thing again, but she points at the 7, the 8, and the 5, and then does a takeaway gesture under the other 5. That's another way to solve the problem. Add up the numbers on the left side, take away the number on the right.
Another way we can solve this. And that is, we can add 7 plus 8 plus 5, which equals 20. And then we want to make the other side of the equal sign the same amount. So 15 plus 5 also equals 20. So 15 would be the answer.
Okay, so we then there were about 20 kids in each group. We gave them instruction, and we looked to see what happened. So first, let me show you what happens on the post-test, varying just one strategy in speech versus two strategies in speech. So teachers tell you that you should give a child multiple strategies, multiple approaches to a problem. That seems like a good idea. But in fact, in this particular situation, it was a disaster. When we gave the kids two strategies in speech, it sort of blew them out of the water, and they couldn't solve the problem anymore. Now I'm going to split these bars into the gesture. And what you see, again, of course, is two strategies in speech is less good than one strategy in speech. But what I said before is not quite accurate. Two strategies isn't so bad if it comes in gesture and speech. That big red bar over there is mismatching, where there are two strategies, one in gesture and one in speech. That actually turned out to be the most effective instruction above all else. Even the same information conveyed in speech didn't work as well. So what this suggests is that gesture is really an effective tool for instruction. But gesture, what I don't want to argue completely that gesture is good for learning. What I want to argue is that gesture is a powerful tool. It can be used for good, but it can also be used for evil. And in this example, I want to show you a way in which it was inadvertently used for evil. So this is the problem, 7 plus 6 plus 5 equals blank plus 5. The kid puts 18 in the blank, and the teacher goes on and says, oh, well, you added up these three numbers to get your answer. And she points at the 7, the 6, the 5, and then the other 5. Then she gives a pretty incoherent explanation, and while she's doing that, the kid says 23. And if you add up all the numbers that she pointed at, you get 23. So watch her.
Yeah, 18.
Is that what you want me to put here? Okay. So you get this answer
That's 18.
by adding
7
these three
plus
numbers.
5, the other 5.
Okay. But you see, there's like 5 here, right? Do you see? So if we put 13, then we have to add 13 plus 5, and that's more than this. Do you see? Because they have to be equal, right? So 7 plus 6 plus 5 has to be the same as, 20. You want me to put 23 here?
And what's really charming about this example, she has no clue as to where 23 might have come from. And maybe it didn't come from her hands, but maybe it did. So before leaving this, effective gestures, other people's gestures on learning, I want to suggest that this is not just a phenomenon stuck on math. This is a phenomenon that extends to eyewitness testimony, and this work done by Sarah Broders, who's sitting right over there. So we all know in eyewitness testimony that we can mislead the witness. And you can mislead the witness by asking misleading questions like, what color was the hat he was wearing? If you do that, you're going to get hat answers, even if he wasn't wearing a hat. So you're supposed to say, what else was he wearing? So what we did is we brought a musician into the classroom. We knew exactly what was happening. Sarah then interviewed the children over the weeks, and she is asking a wonderfully open-ended question. Now, all you really need to know in listening to this is that the musician was not wearing a hat, okay?
Okay, what else was he wearing?
A music hat.
A music hat? Was he wearing anything else that you can remember?
Yeah.
Yeah.
A green hat.
A green hat?
No, queen hat.
A queen hat.
And cowboy hats, too.
So there's a plethora of hats, not just one hat. So where the hell did all the hats come from? Well, if you look at Sarah carefully, what she's doing,
Okay, what else was he wearing?
she's doing this great open-ended question, but she is targeting it with her gesture. And it turns out we got just as many hat answers to what else was he wearing as to what color was the hat he was wearing. Gesture being very powerful, and just for the record, the legal world ignores it. So we don't know necessarily when our interviewers are misleading our witnesses. Okay, so gestures we see can change our minds. How about the gestures that we produce? Again, we have to manipulate gesture in order to be able to say it's playing a causal role. So we taught kids, one group of kids, to say, I want to make one side equal to the other side, and they had no gestures to produce. They had to say this before and after each problem that they solved. Here's an example.
I want to make one side equal to the other side.
Okay, now you put your answer in.
Okay, the next group said exactly the same thing, but what they did was they pointed at they put a V under the first two numbers and then pointed at the blank, a grouping strategy, which works perfectly well to solve the problem.
So first of all, can you say the words and do the hand movements exactly like we practiced?
I want to make one side equal to the other side.
Okay, now can you put your hand?
Okay. Now, to control for the movement, because those two groups vary in terms of whether one's producing movement, one isn't, we had another group. We told them to put their V under the wrong two numbers and then to point at the blank.
Do the hand movements exactly how we practiced?
I want to make one side equal to the other side.
Okay.
So this is an important condition, because if all gesture is doing is pointing your direction in terms of, at a particular number, this should be a disaster. They're pointing at the wrong two numbers. But if gesture is giving you a bit more information, grouping in your two hands, and the fact that there are two sides of the problem, it's not fully correct, but it's partially correct. Okay, so let's see what happens. All the kids got the same lesson. It was a pretty complete lesson. We really didn't just put them at C. And this is what happened. This is the post-test performance. They were all at 0 on pre-test. Over here, the kids who got fully correct gesture, that is, who produced fully correct gesture, did the best, then partially correct gesture, and better than no gesture. And what we think is going on here is that the kids were extracting meaning from their meaningless gestures. Initially, they're just producing these movements. They have no idea what they're doing. But over time, they sort of come to understand that that's grouping. And the reason we think that is because at the end of the day, they start saying grouping. So here's a kid who starts saying grouping for the first time at the end of the study.
The 6 and this 6, since there's 2 6, I know, so I shouldn't use this one, so I added these two.
He's really got it. He knows the two addends. I mean, he's really got it. And he got it by using his gestures, because remember that the experimenter never produced grouping in speech or gesture, and the kids never produced grouping in speech, only in their gestures. So we really think is the grouping is coming from the kids' own gestures. Okay, so now I hope I've convinced you this is worth investigating. Now let's try to think about why. Why does gesture work? So what makes gesture a mechanism of change? Well, one of the things that's really salient about gesture is that it's an action. It's an action of the body, and we know actions are good. They help us remember, they help us learn. Maybe gesture is good because it's an action. So what I want to do is tell you 3 ways in which gesture is an action and helps learning. But then I want to go on and suggest that the story is more complicated. So first I'll give you the straight story, then I'll complicate it. So gesture engages the motor system. Obviously, gesture engages the motor system when we're talking. It's a no-brainer. But the question is, does gesture engage the motor system when you are watching me, as I'm wildly flailing my hands up here? Or is your motor system engaged? Okay, that's the question. How do we answer that question? And in order to do that, we have to have an online measure of gesture processing. So we developed one. We used a technique developed by Rolf Zwan. And people hear the sentence, the girl put the towel back in its place, and they have to decide whether this object, whether this thing pictured here was mentioned in the sentence. Now, if you had in your mind that it was a towel stuck on a hook, you'd say yes pretty quickly. If you had in your mind that it was a towel folded up like that, you'd say a little less quickly to that picture, but a little more quickly to this one. And that's the mechanism's work. We're going to try to push these people around by virtue of the gestures they see. So they didn't just hear the sentence, they saw this.
The girl put the towel back in its place.
Okay, so when they saw that, they should say yes very quickly to that picture, and yes a little less quickly to that picture. Remember, it's yes. They have to say yes in both conditions. Okay, as opposed to this.
The girl put the towel back in its place.
Okay, great. So here you say yes to this one a little more quickly, then you say yes to this one a little more slowly. And that is exactly what we found. So there we have reaction time to the picture. The congruent pictures are in blue, faster reaction time, than the incongruent pictures, which are slower reaction time. Okay, so now we know people are processing gesture. Great. What do? Our hypothesis is that listeners are activating their own motor systems when they're listening to somebody who's gesturing. And if they are, let's load up those motor systems. If we load them up, that should get in the way if they're really processing the gesture in that way. Okay, so we asked adults to plan and produce arm or leg movements. We thought arms should interfere, that's the same motor system, legs should not. So they did exactly the same task, and they had to make movements. So here's an example of somebody making hand and arm movements. She's very delicate and lovely. And those, we're hypothesizing those should interfere, as opposed to our foot movers, who some of which were elegant, this one wasn't particularly, should not. Okay, so what happens? In the arm movements, it went away. The effect went away, the congregation effect. But it isn't just because they were doing something, because when they're moving their feet, it was fine. You got exactly the same congruency effect. So that suggests they are processing the gesture, and when they're moving their hands, that's getting in the way. So don't fidget too much. You're not going to be able to understand. Okay. Okay, so the motor system is involved not only in producing our gestures, which is sort of obvious, but also in understanding the gestures that others produce. Okay, so it engages the motor system. It also leaves a motor signature. So we know that learning through action actually leaves a motor signature. So kids who learn by acting on something, say writing out letters, as opposed to somebody else watching somebody write out letters when they're trying to learn letters, they, of course, are establishing neural representations as they're doing that writing. But the interesting thing is that a week later, or a month later, when they're asked to come in, sit in a scanner, and just recognize those letters, you see those same neural systems being activated, the motor system. You see a motor network being activated. So having learned through action, you see an effect a week later in the motor signature. Do we see the same motor signature for gesture? Well, we taught kids this equalizer strategy when speech alone.
I want to make one side equal to the other side.
Or in speech and gesture.
One side equal to the other side.
Okay, and then we took only the ones who knew what they were doing, who had learned, and we brought them back a week later for an fMRI session. We stuck them in the scanner, and in the scanner, they solved a problem in their heads, and when they finished solving it, they pressed go, problem disappeared, it reappeared with an answer, they had to say yes or no. Okay, so passive, no moving at all. And what we found is that for the kids who had learned using speech and gesture, we found much more activation in these areas than in speech alone. And those are precisely the same motor areas that you find in action. So what that suggests, and there's the motor network there to show you, it's not actually totally identical. So learning through gesture leaves a motor signature, and it's not totally identical, which sort of is exciting to us now because we're now going to start exploring the ways in which it's the same and different from gesture. And that's actually step 2, but let me get there in a minute. Okay, so first I want to tell you how gesture adds information, action information to our representations. This is work done in conjunction with Sion Beilock. And our hypothesis was that gesture brings action information into the gesturer's mental representations. And if so, people's thoughts about a task ought to change in predictable ways when they themselves gesture. So we use the Tower of Hanoi task, which I bet everybody knows what it is, but just in case you don't, you put discs on one pole, and what your job is to move all of those discs from one pole to another pole. You can only move one at a time, and you can't put a big one on top of a little one. So it's really a logical puzzle. We had people solve it with real discs. And after they solved the 4-disc problem, which actually was not so trivial, they had to talk about it. And of course, they gestured, because that's the way it goes.
So there were 3 pegs, and then so there was 4 discs on this peg. And so then I moved the top disc. They were in order from big to small, from bottom to top. And so I moved the top smallest disc to the middle. And then I moved the second.
Okay, so after having solved it, having talked about it, they were asked to solve it again. And we divided them into 2 groups. One group, the no-switch group, got exactly the same 4-disc problem, and they did fine, they improved. The other group was a switch group. And now we switched it. So this big one, which was so heavy you had to lift it with 2 hands, now you could lift with 1 hand. And the little one, which was really light, now you had to use 2 hands. And what we're interested in seeing is whether your performance at the end of the day here, after you talked, was influenced by the gestures you produced while you were talking. Because if you gestured about that little one with 1 hand, you're setting yourself up for failure because you can't lift it with 1 hand. You need 2 hands. Okay, and some people gestured about it with 1 hand. Here's this woman actually gestures about the little one
The top smallest disc to the middle.
with 1 hand, but this guy gestures about it with 2.
Taking the smallest disc on the top and putting it on the middle.
Okay, so what happens? So this is the performance. I'm giving you here the difference score between the second trial and the first trial. The no switch group gets better. Going down is better in this case. The switch group does not get better. But importantly, you get much, not more, not better, the more you gesture with one-handed. So over here on the right, you have more one-handed gestures, and the more you do that, the worse you are. That's true in the switch group, but it's not true in the no switch group, because of course you can lift with one or two hands, it doesn't really matter. Okay, so I'm arguing here that gesture's changing representations, but maybe it's just reflecting it. That's possible. So if gesture's really changing knowledge, we should find differences between these groups only when you get gesture. So what we really wanted to do is say, okay, explain it, but don't gesture. It turns out if you ask people to explain this problem and not gesture, all hell breaks loose. They fall apart, they can't do it. It's really impossible to do it, which is interesting in and of itself. So what we did is we did the study again and we said, don't explain it. Just don't explain it. So they did it once, then they did it again, and we had the switch condition. Okay, and this is what happened. Over here, what you see is the data I showed you before, but when there were no explanations, there's no difference between the switch and the no switch groups. Pretty impressive, because we're switching the discs on them. They're now finding, they have this big disc that they can lift with one hand. It has no effect. The only time it has an effect is when you gesture, and when you gesture about it in a way that's not consistent with your subsequent performance. Okay, so gesturing adds action information. If the action information is compatible, terrific, you go on and you can solve the problem. If it's not, performance suffers. And this is an interesting thing because weight is totally irrelevant to how this problem is solved. Nobody ever talks about weight because it's irrelevant. But if you're gesturing, you have to use one hand or two hands, or you're not gesturing. And one hand versus two hand sort of it brings weight into this implicitly, and that sneaks in and it seems to affect how they're thinking. Now, one more point here. Gesture can be more powerful than action itself. We did this again, and instead of having people gesture, we had a condition where they did it once, they did it twice, and then they had the switch condition. And what we did was we compared the people who just did it again versus the ones who gestured while talking. And we made sure that they were using one hand to gesture versus one hand to move that little disc about the same number of times. And what you find is the same effect. We replicated it, but in the action condition, no difference. It's not just about moving your body, which I think is really important. Gesture is an action, but it's a special action. And it actually can be more powerful for learning than action itself. Okay, so that is the beginning of the complication in this story. So I want to tell you now 3 ways in which the story is much more complicated and gesture actually goes above and beyond action. So first, let me talk about the ways in which it leads to generalization. Okay. So gesture's grounded in action. It's really movement and you're doing things. But at the same time, it's representing something. If I do this, I can do a twist gesture. I can do it till the cows come home. I'm never going to get that jar open. The only way I'm going to get that jar open is to put my hand on the jar and twist it open. Unless, of course, you take pity on me seeing my gesture and you open the jar, unless you interpret my gesture as a representation. So maybe gesture can take a learner from an action, a concrete event, and sort of help him transition to something that's more abstract. That's our hypothesis. So we taught kids again to make these ridiculous words. I want to make one side equal to another side. And we varied the concreteness of their actions. So in the first condition, we put these numbers on top of the real numbers, and the kids literally had to do grouping. They picked up the 5, they picked up the 7, and they held it under the blank.
One equal to the other side.
So it's literally reenacting the grouping strategy. These guys did the same thing, but they didn't touch the numbers.
I want to make one side equal to the another side. Okay.
Okay, and this last one did this abstract gesture that you've seen before. No, you're going to see it now.
I want one side equal to the other side.
Okay. Then we gave them a post-test. And on this post-test, we varied how hard the problems were and how much they were like the problems on which they were trained. So if you're trained on a problem like this, the blank is to the left. And then the trained problems, you get a bunch of those, not the identical problem, but problems like it. And it's easy. You can solve the problem by adding the first 2 numbers, just like you were taught. We also gave them near transfer problems where we moved the blank to the right. got to be smarter now. You have to have known more. You can't just rotely add the first two numbers. You have to group the second two numbers. You have to know which numbers to group. And in the FAR transfer problems, we took out the equal addends entirely. And now you really need to understand the problem. You need to understand mathematical equivalence in order to solve this. Okay, so let's see what happens on the trained problems. So here are the three conditions. There were no differences, which is actually nice. Action is great for learning. Gesture is great for learning. The problems on which you were trained. Now let's look at the near transfer problems. And here it starts to get interesting because action drops off. But gesture is still very good. These are the proportion of kids who succeeded on the trained problems and also succeeded on the near transfer problems. And you can see that it's a high proportion in both the concrete gesture and in the abstract gesture. Interestingly, when we get to the FAR transfer, even the concrete gesture is falling off. So what this means is that action is just fine for learning the problems on which the children were taught. But if you want children to generalize what they learn, which sort of is what we're about here, you need to think about it because action is tying them to that problem, whereas gesture may be freeing them to port that knowledge to another problem. Okay, so gesture helps them generalize, action doesn't. Gesture represents information, action doesn't. So why does gesturing lead to change? One possibility is that it's hand and mouth. You're using your hand, you're using your mouth. Two modalities together are better than one. The other possibility, however, is that these two modalities represent information in different ways. So speech is categorical, discrete. Gesture conveys information in a more mimetic, analog way. Maybe it's the juxtaposition of these two different representational formats that really is giving gesture its power. Now you can't ask that question in hearing people, because when we gesture, we use our hands, we talk with our mouths. But you can ask this question in deaf people, because deaf signers gesture, as Karen Emery showed many years ago, and their gestures are continuous, they're mimetic, they're analog, whereas their signs are categorical. So if it's hand and mouth that's the issue, it shouldn't work with deaf people. But if it's the juxtaposition of two representational formats, it should work just fine. So the question then is whether signers produce these gesture sign mismatches, and if they do, whether those mismatches predict learning. Okay? So let me show you what a gesture looks like for a deaf child. This is a child doing this problem, and with her signs, what she does is she says, add all. So she does add all. And with her gestures, she points at all four numbers. She's doing exactly the same thing in gesture and in sign. Here she goes. There's a gesture, add all, more gesture. Okay? So here's her signs, add all, and her gestures, bunk, 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 bunk. Okay, so it's exactly the same information in both gesture and in sign. Now, the kids produced 80% of the problems had gestures for these deaf kids. Is that a lot or a little? We don't know. We went to the hearing kids to find out, and the hearing kids produce about 73%. About the same. But the crucial question is, do they produce mismatches? What does a mismatch look like in sign? I'll show you. This is a mismatch. What the child does here is she adds up. She does add and puts it in the blank. So adds up the numbers on the left side and puts it in the blank. But while she's doing that, she's covering that 7, which is the equal addend, with her gesture, which is sort of like an add-subtract strategy. Okay, so watch her. It's very fast. Okay, so with her sign, she's doing add and put it in the blank. With her gestures, she does add, but she's covering that 7, which is like an add-subtract strategy. So it's really a mismatch. So 42% of the kids produce more than 3 mismatches, which is roughly comparable to what we find in the hearing kids. Okay, but now the crucial question is, does that predict learning? So what I've done here is I've arrayed on the bottom the children as a function of how many mismatches they produce prior to learning. 0, 1, 2, 3, 4, whatever. And what I'm going to show you is the proportion of children who succeeded after learning. They have to get 5 or 6 problems right out of 6 in each of those bins. And what you see is a really nice pattern, because the kids who produce very few mismatches over there are not very likely to learn. Very few of them learn. On the other hand, the kids who produce 6 mismatches prior to learning basically nailed it. Okay? If I put it in the same format as the hearing kid data I showed you initially, you see exactly the same effect. So what this really suggests, it's not about hand and mouth. It really isn't. It's really about the juxtaposition of these two different representational formats that seems to be really important in giving gesture its power. Okay, finally. Gesture's tied to speech, action isn't. You know, when I'm talking in gesture, we're basically sort of talking about the same thing, but I can talk about anything while I'm drinking my cup of coffee. It's not tied to speech in the same way. Is that important? We tried to find out by manipulating the gestures that children see. So we gave kids gesture with speech. This is actually the same sort of thing you saw before in the Melissa Singer study. The teacher says equalizer in speech and does add, subtract in gesture. I'll show it to you one more time.
So we can solve this problem by adding 7 plus 8 plus 5, which equals 20. And then we want to make the other side of the equal sign the same amount. 15 plus 5 also equals 20. So 15 is the answer. Okay, so now I want you to try to solve it.
Okay, so then we spread it out. We did speech and gesture, exactly the same thing. And to make it not weird, she says, now watch my hands.
So we can solve this problem by adding 7 plus 8 plus 5, which equals 20. And then we want to make the other side of the equal sign the same amount. 15 plus 5 also equals 20. Okay, so watch my hands. So 15 is the answer.
It's easier to process
so
that,
I want
actually.
you to try to solve
Get it one at a time, it's easier to go. And then finally, the last condition, we had speech, then speech, equalizer in speech, add, subtract in speech. I'm not going to play this because it takes too much time.
Okay.
You can imagine. Okay, so what happens? This is retention over time. I'm showing you here. We gave the kids a post-test immediately after training, 1 day after training, 4 weeks after training. And what I've shown you here is just the two conditions that are most extreme. Gesture with speech in red, speech then speech in white. Of course, speech then speech. You can't put speech and speech on top of each other. Okay, and I showed you this earlier. Gesture with speech is more effective than speech and speech. Okay, and it's effective immediately after training. You see this effect. 1 day later, you see the effect get stronger. 4 weeks later, it even gets more strong. So it's sort of interesting. If you look at this, the speech then speech, if anything, is getting worse, but the gesture with speech is improving. They're getting better over time from having learned from gesture with speech. Question now is, what happens when you split gesture and speech and make them sequential? Any guesses? Turns out it doesn't work. I don't know if that's what you would, it wasn't what I was going to guess, actually. I think it's really very interesting that you see, when you split this, it's not just about the two modalities, they have to co-occur, which in some ways, it's much harder to process. And we see the same effect for the generalization effect. So this is immediately after training. Immediately after training, what we see is that a very small effect for speech with gesture on the trained problems, but the near transfer problems, you already see it getting a little bit bigger, and the far transfer is where you really see it. But a week later, already here on the trained problems, you see it, and certainly in the near transfer and the far transfer. And 4 weeks later, what we see is a very big effect of speech with gesture. So having these two representations is best when they co-occur. It means that we process them at the same time, and it's important that we process them at the same time. Okay, so just let me briefly summarize. The gestures we produce provide a window onto our thoughts. That window actually often gives you a different view from the window that speech gives us. And importantly, this window not only reflects what we know, but the gestures we produce can change what we know. It changes our minds. Just by virtue of it, you've got to be careful about how you move your hands, because as you're moving your hands, you're changing the way you think. And importantly, gesture is an act of the body, which I think is very important, but it may be important not just because it's embodied or motor or whatever, but it could be because of the representational potential that gesture provides, rather than the fact that it's done by the body. Okay, so I just want to end by a quote from William James. William James had something apt to say on every single topic, and he had something very important to say about action as well. Action may not always bring happiness, but there is no happiness with action. And I would just like to make a friendly amendment to that. As you might guess at this point, gesture may not always bring happiness, but there is absolutely no happiness without gesture. So I want to end by thanking my many, many collaborators, thanking you for listening, and of course, watching my hands carefully, which I'm sure you all did. Okay, so we have time for questions, which is great. I know, I talk really fast. Might be too bad. Yes, Rochelle. All right, she's going to bring the mic.
In watching the arithmetic, I think of an experiment. I wouldn't say it's a control so much as to say what the representation is.
Okay.
Brackets.
Brackets, yeah.
Mathematics uses brackets.
Yep.
Just as the gesture's being used.
Mm-hmm.
And so
Right.
I think it'd be very interesting to see what happens if you use brackets
Right.
separately.
Right, right. A visual grouping, in a sense, right? That's what you're really suggesting, a visual.
And I call it visual because it's part of the symbol system of mathematics.
Right, but it's conveyed
It says
visually.
what goes with what.
Right, that's right. That's right. And that's, in a sense, what I'm doing with the hands, too. No, I agree. I agree. But I think what we're trying, at some point, we've been trying, we haven't done it with brackets yet, but we've been trying to look to see whether a visual representation works just as well as this motor representation. So we've done this actually with teaching polynomials. And we've had children see somebody gesture while the teacher's doing it. Or we use a highlighter, which tracks what she does just the same way. And it's really not effective. So I don't know. I mean, I think it's a great question, and we really need to do it at some point. I mean, it wouldn't mean that gesture's not important, but it would mean is that there are other ways of getting there. Right, that's right. Right. Right, right. I honestly don't know how important the body is in all of this. And we're just trying to push this around a little bit to see by doing things like this, by giving them different kinds of input. So I think it's a really important question. Thanks. Yeah.
I can do it without. It's all right. What kind of learning do you see in quadriplegics?
In
Quadriplegics.
That's, of course, the perfect question. I mean, you know, I would not want to predict that they can't learn, because that would be a very stupid prediction. So I've got to say that there is, of course, other ways of getting there. I don't know what kind of imagining they're doing. You know, quadriplegics have moved before. More interesting would be people who have never moved at all. They might follow different routes to learning, and there might then be different end products, and those would be very interesting to look at as well. But I don't want to say that this is the only way to learn. I mean, I think that, you know, learning visually or whatever is important, but I think it gives you a special kind of learning, and you see the effects of that post hoc, you know, when you see this motor signature. Yes?
Selective interference study, when the woman with the very graceful arm movement
Yeah.
was moving her arms, the interference of the anti growth effect didn't go away. But both of those conditions were faster than either of the conditions when she was moving her legs.
Right.
So
right.
is there some kind of load that's put on to process these things?
I think there is. I mean, there is definitely an effect of the level. You're absolutely right. And so the feet are, yeah. We have no explanation for that, but you may have some explanation for that. Basically, it's the difference, you know.
Well, you yourself were saying you think there's a whole lot more information to process. Even though you might get some
Right.
benefits from it, but the real-time processing might
Right.
actually stress capacity.
Right, it might. It might, right. Yeah, so the whole reaction time is different. The level is different in the leg moving than in the arm moving. Yeah, you're right.
Hi, does the use of gesture here...
Where are you?
Hi. Does the use of gesture increases with the difficulty of the task?
Yeah, I think it does. Nobody's done that study really well. Oh, sorry. Does the rate of gesturing increase with the difficulty of the task? And it typically does. There's good evidence for this, although people haven't really explored that question per se. But it should, if you're doing this, if it's really helping you learn, then as the difficulty increases, you should up your gesturing, and it does. Yeah.
Tell physicists who are experts that they can't use their hands. They can't do it.
Right.
Physicists, they can't do it.
That is true. I mean, if you look at physicists, chemists, geoscientists, any scientist, and watch how they explain their problems, they can't do it without gesturing. It's really, really important part of their thinking. Yes?
Yeah, we're developing educational interventions for the iPad and trying to leverage gesture.
Yeah.
And what I didn't really think about until your presentation is that we're trying to use deictic gestures versus representational gestures, but we're not having them speak while they're doing the gestures in the context of
Okay.
the game. Can you comment on that?
Yeah, we should talk, actually.
Okay.
We should really talk about this, because
Okay.
we're also doing an iPad study. I don't know. I know we have a nice effect here when you're watching gesture, but when you're producing gesture, I'm not sure it's going to work in the same way. So we're doing that study right now, so I'll let you know. But I think this whole idea of doing something on the iPad versus the gesture is really interesting. We've done a mental rotation study where the kids can rotate. Are you doing that too? Yeah. No. Oh, that's what he's doing. Okay. Where you do a mental rotation, you can actually touch the iPad, and gesture is much more effective than the iPad is. And so we should talk about this. I think this is a really interesting way to go. Yeah.
Towards the end of your talk, you mentioned that gesture-coupled speech actually led to increasing retention.
Yeah.
You given thought to that?
I think it's probably, it's laying down a neural trace, which is then being reactivated. Of course, that's not good enough because it's presumably, I don't know why it continues to grow. That, to me, is the more interesting question, not just the retention, but now maybe it's just that they learn it and they start to actively apply it. I don't know, and I'm not even sure how to explore that. Like, why does it help you grow? But we found it in other contexts as well, where doing the gesture continues to, it's a gift that keeps on giving. And if you have any good ideas about how to pursue that, I'd love to hear them.
Susan?
Yes.
Hi. So really it relates to that last question about the overlap between gesture and the speaking at the same time, the co-occurrence. So I'm wondering if part of that answer comes from studying deaf children because they can't gesture and sign at the same time. So they do have to disambiguate the timing of gesturing and signing. So I'm wondering how they can manage that, if that gives you some clue as to how they can manage the coupling with the language and the gesturing.
Yeah, so I think that's a great question. I think, and it's going to really push me hard to think about what do I mean by the timing? Because at some level, those little girls that I showed you were actually integrating their gesture into the sign, but it wasn't completely simultaneous. So what do I really mean by that? And I think you're right that the deaf kid situation is going to force us to think hard about this. And the deaf situation is great for just trying to figure out how to separate gesture and sign to begin with. But thank you. Yes, I completely agree. One more. Okay.
A neuronal print that's left with
action and
actually writing.
Uh-huh.
Do you think the same thing happens like typing on a keyboard or?
I would guess
doing
so.
with the
I would guess so.
smartphone?
I mean, this is work done by Karen James, and she's done it in
Karen
other
James.
contexts. I don't think she's done typing on a keyboard, but I think she's done a variety of problems. So I think it is an action. And what we're doing this work right now, we're comparing learning by action versus learning by gesture, because what we think the action is doing is tying you to that instance, whereas the gesture can be freeing you to abstract. And so we're thinking that we'll see different activation in areas that are more higher order thinking, abstraction for gesture, not for action, whereas we'll see areas for visual processing or object processing for action, but not for gesture. So we may be able to explore that hypothesis in our fMRI data. That's where we're going next.
Right.
Okay, thank you very much.